Welcome friends to the next session of turbo machinery. In the previous session, we have seen the introduction part of the turbo machinery and some of the applications in it. Now moving ahead, in this session, we will see some of the basic concepts of turbo machinery and some of the process related to it. First, we will see the impulse momentum principle. When jet of water strikes on a flat plate, it exerts a force in the direction of jet which is equal to rate of change in momentum in that direction. So the force is equal to rate of change in momentum. The change in momentum means initial momentum minus final momentum, and the rate of change in momentum is initial momentum minus final momentum per time. Now momentum is mass into velocity. So the equation of force becomes mass into initial velocity minus mass into final velocity divided by time. Taking out the mass and the time outside, force is equal to mass upon time into initial velocity minus final velocity. Now we will see the force exerted by the jet on a stationary vertical plate. We can see here a vertical fixed plate normal to the jet, and a jet is striking on the plate coming from the nozzle. Let V is the velocity of the jet, D is diameter of the jet, and A is the cross-sectional area of the jet. The force exerted by the jet on stationary vertical plate in the direction of jet is given as force is rate of change of momentum in the direction of form. So the force is equal to initial momentum minus final momentum divided by time. So finally we get the equation mass upon time into initial velocity minus final velocity. Now taking time as 1 second and mass can be written as rho AV, the equation becomes F is equal to rho AV into the bracket V is the initial velocity and final velocity is 0. So the force is equal to rho AV square is the final equation for the force exerted by the jet on stationary vertical plate. Similarly, we will see the equation of force exerted by the jet on stationary inclined flat plate. I repeat, stationary inclined flat plate. So here in this diagram, we can see an inclined fixed plate with an angle of theta to the vertical, and a jet is striking the plate, inclined plate, coming from the nozzle. Now the mass of water striking the plate M can be written as rho AV as we have seen in previous slide. Now let theta is the angle between the jet and the plate. V is the velocity of jet, D is diameter of the jet, and A is cross-sectional area of the jet. The force exerted by the jet on inclined flat plate in the direction normal to the plate is given as force is equal to mass of the jet striking per second into initial velocity of the jet in the direction normal to the plate minus final velocity of the jet after the striking in the normal direction. So the equation becomes force is equal to rho AV, where initial velocity is v sine theta and final velocity is 0. So the final equation becomes rho AV square sine theta. This force can be resolved in two components, one in the direction of jet and other in the perpendicular direction of jet. So the force in the direction of jet can be written as Fx equal to F into cos 90 minus theta, so which becomes F into sine theta. Taking the value of F from the above equations, we get the final equation as Fx equal to rho a v square sine square theta. Similarly, the force in the normal direction of jet Fy is equal to force into sine 90 minus theta, which becomes F cos theta. Again, putting the value of force from the above equations, we get rho a v square sine theta cos theta.